Today's topic is molecular vibrations. My cat Onyx really likes to stretch. Molecules like to stretch too. They stretch, they bend, they flex. We call these motions molecular vibrations. In fact, even at 0 Kelvin, molecules are still vibrating. How can that be? At 0 Kelvin, you're not supposed to have any thermal energy, right? Well, quantum mechanics actually requires that molecules vibrate. Otherwise, we might know the position and momentum of the atoms at the same time, and Heisenberg's uncertainty principle tells us we're not allowed to know that. And so Heisenberg's uncertainty principle forces the molecules to vibrate even at 0 Kelvin. And the energy of vibration that they have due to this is called the 0 point vibrational energy, or sometimes just the 0 point energy. So today I want to tell you a little bit more about how molecules vibrate and then how we can model that using computational chemistry. It turns out, fortunately, that at least for small molecules, we can do high accuracy calculations and model molecular vibrations very, very accurately. Now, why would you want to do computations of molecular vibrations? Well, you might want to simulate a spectrum to help you identify a molecule. I'll show examples of that a little later. You might want to compute the vibrational contribution to the enthalpy, and that would be necessary if you want a very accurate enthalpy. You need the vibrational piece of that. We'll talk about that at the end of the talk. In principle, vibrations cause small corrections to other properties like polarizability. We won't discuss that explicitly today, but that is an issue if you're trying to compute those properties very, very accurately. Just understanding the vibrations of a molecule tells you more about how it's bouncing around and how maybe you could take advantage of that knowledge to do what's called mode selective chemistry, where you try to push the molecule in some direction or another by picking out some particular vibrational mode and encouraging that kind of vibration. The best book that I know about for molecular vibrations, if you're interested in the details, is a classic work by Wilson, Decius, and Cross called Molecular Vibrations. It's available as a cheap paperback book by Dover, and I encourage you to pick it up if you're at all interested in the mathematical details. I'm going to show a few equations from their book just to give you a bit of the background, although I won't go through them in a huge amount of detail. But like Wilson, Decius, and Cross, what we'll do is first talk about the classical mechanics of molecular vibrations, and then we'll focus in a little bit more specifically on how to model this with quantum mechanics. So first off, imagine I've got a molecule and I have several atoms, and each of those atoms can be moved in the X or Y or Z direction. And that's true for every atom. So I'll denote those displacements from the current position as delta X alpha, delta Y alpha, and delta Z alpha, where alpha is going to index the atom that I'm talking about. And that'll run from 1 up to 3n if I have n atom, or 1 to n if I have n atoms. But for each of those n atoms, I have 3 coordinates, delta X, delta Y, delta Z. Now, I can write the kinetic energy easily enough because that's 1/2 mv squared, and I have n particles. Each particle, or each atom, has a mass, which I'll call m alpha. And so what's v, the velocity? Well, the velocity is just how much I'm moving in a unit of time. So it's the change in this displacement, d delta x alpha, for example, dt. And that's the velocity in the x direction for atom alpha. and then I square it to get 1/2 mv squared. And I do the same thing for y and z for each atom, and I add all those up, and that gives me the total kinetic energy. Now, a lot of times what people do is switch to what's called mass-weighted coordinates. This isn't necessary, but it's something that pretty much all derivations do, just because it keeps the math a little bit cleaner. So what we do is we define a new set of mass-weighted coordinates, which we call Q, and we just multiply each of my delta displacement coordinates by the square root of the mass of that atom. So Q1, for example, the mass-weighted coordinate for the displacement in the x direction of atom 1 is just delta x1 times the square root of the mass of atom 1, m1. And I go ahead and number these consecutively. So Q2 will still be atom 1, but it'll be in the y direction. Q3 will still be in the, for atom 1, but in the z direction. And then Q4 then starts me on to atom 2, and et cetera, et cetera. All right, in that scheme, then your kinetic energy operator can be written in a much more simple way as 1/2 the sum over all these mass-weighted coordinates, qi dot squared, where the dot's going to mean a time derivative. So those are the velocities in the mass-weighted coordinates. And now I don't need an m because it's been sucked up into the q coordinates. Now the potential V, I'm going to write as a Taylor series, some reference energy V naught plus the gradients times all these mass-weighted coordinates, plus 1/2 times the Hessian times the products of all these coordinates. And in principle, we could keep going, but we'll normally terminate this series at just the second derivatives. Although you would need third or fourth derivatives if you want high accuracy. But for now, we'll stop it at the second order derivatives. And at equilibrium, if I'm at the bottom of some potential well, then the gradient will go to 0. And so delta V, delta Qi is going to be 0 if I'm at the equilibrium position, denoted with subscript 0. In general, for some classical potential, I'm free to set the energy of the 0 point, of the equilibrium point, as 0 as well. The second derivatives, I'm going to go ahead and denote Fij just so that my notation is a little bit shorter. So then what I'm going to do is essentially write F equals ma, but I'm going to write it in a little bit of a fancier looking form. The time derivative of the partial derivative of the kinetic energy with respect to one of these q dots, plus the partial derivative of the potential with respect to one of the q coordinates equals 0 for all possible mass-weighted coordinates. And if I do a little bit of calculus on that, and take those derivatives and go back to the previous slide and look up what t and v were again, with a little bit of work I can show that the second time derivative of one of these mass-weighted coordinates, qj double dot, plus a sum over all the coordinates qi times fij equals 0 for all possible j, running from 1 to 3n. So that's my set of working equations. Now, this is a bit of a nasty equation because it's a set of coupled differential equations, but we could sort of hope for the best and guess a solution like sines, cosines, or exponentials, which are frequently solutions for equations like this. The coupling Fij makes us a little nervous, but if we kind of ignore that for a second, and just imagine I had qj double dot plus some constant times qj equals 0, then I'd say, well, it's a sine or cosine or exponential kind of solution. Here I'm going to guess qi is some coefficient ai times a cosine function, and I'm going to go ahead and write square root of lambda t because I kind of know where this is headed, and then I'll put in a phase factor phi. You could make it a sum of sines and cosines if you wanted, but we'll use cosine with a phase factor phi. So the angular frequency, which we might write omega, here I'm writing square root of lambda. In a one-dimensional problem, this would just be the harmonic oscillator, which is the square root of k over m. Now, m I don't have here because it's been absorbed in the q coordinates. Now here I don't have a one-dimensional problem, I have a multi-dimensional problem, which is all coupled due to that Fij. But if we go ahead and guess this simpler solution and plug it in to my set of working equations and do a little algebra, what I find after the substitution is I get this set of equations. So there are 3n equations, one for each coordinate, and I get that Fij minus Kronecker delta ij, which is just 1 if I equals j, or 0 otherwise, times this value lambda, times some coefficient ai that I had on the last slide, equals 0. And so all of those nasty coupled equations become uncoupled and give simple solutions if this equation is true. Or in other words, if I pick those values of ai and lambda such that this equation is true, and if I rewrite this as kind of a matrix equation rather than this form, then in matrix notation I have matrix F, whose elements are just Fij, times this vector A equals lambda, some number, times vector A again. And if I took lambda A from the right-hand side to the left-hand side, I'd subtract it, and then it would look more like the equation above. That's just a normal eigenvalue equation. So the eigenvalues lambda and the eigenvectors A are very special values. They're so special that they basically diagonalize the matrix and give me a set of uncoupled equations, which were formerly all coupled to each other. So this is really great. Another way of finding what are the lambdas such that this is true is to solve the secular determinant, which I've written below. So if I write out the determinant of f where I subtract lambda from the diagonal, those lambdas where that determinant equals 0 will be the ones that solve the equations that I want. What I'm asserting is that solving my set of equations is equivalent to finding that basis of eigenvectors that diagonalize the matrix F. And the eigenvalues lambda that go with those eigenvectors. So in the eigenvector basis, F is diagonal, the equations all uncouple, and I just get a harmonic oscillator-like picture for each of the possible modes of vibration. Now remember, there are multiple solutions. If I have a 3n by 3n matrix F, of force constants, then in principle I have 3n possible eigenvalues and correspondingly 3n sets of eigenvectors that go with those eigenvalues. So here in this set of solutions, I'm numbering each solution. There are 3n solutions with k, and then within each solution I have 3n atoms that are moving in some direction, and how are they moving? Well, that's given by qik. So for the kth normal mode, qi tells me what each of the I mass-weighted coordinates is doing, and remember I've got 3 mass-weighted coordinates for each atom. The atom moves by some amount. The maximum amount is given by aik. Cosine is always going to give me a value between -1 and 1, so it could move either positive or negative aik. And how far does it move? Well, it depends on the amplitude aik as well as what time you're at, because I've got a harmonic motion. It's moving back and forth between minus aik and positive aik in the x, y, or z direction for that atom. And then I just plug in the time multiply it by the square root of lambda k, add the phase factor, compute the cosine, and then multiply it by that aik. So what's really interesting, if you think about this for just a second, is that all of the atoms are moving back and forth at exactly the same rate, because the rate is given by square root of lambda k times t. And that's true for every atom in the system, and the phase factor is also the same. So all the atoms in the entire molecule are moving collectively at the same rate, even though they might move by different amplitudes. So the AIKs can be different, but the motions are all in step. And we could call these eigenvectors AK the normal modes. And for each normal mode, all the atoms are moving with the same frequency and the same amplitude. So, knowing all this, I could define a new set of coordinates. I'll call them capital Q this time. And they're just a combination of my original simple Q coordinates, the mass-weighted coordinates on each atom, times these amplitudes that I get from getting the eigenvectors of the force constant matrix. And so this gives me a set of normal coordinates. Because the eigenvectors of a real symmetric matrix are orthogonal, then it turns out the kinetic energy operator T and the potential energy V become diagonal without any cross terms. And so T is a simple sum of 1/2 capital Q dot squared for each coordinate k, going from 1 to 3n. And V similarly is 1/2 a sum over all the qk squared times lambda, the eigenvalue. And it turns out that if you are able to write it this way, then you can see that T is a simple sum of independent coordinates, V is a simple sum of independent coordinates, and whenever you have sums of independent coordinates in quantum mechanics, then the Hamiltonian is separable. And so this sets us up to be able to transition from the classical picture to the quantum picture, because it's going to be very easy because we have a separable Hamiltonian. Before I move on and talk about the quantum solution, let me just say a little bit more about these normal modes of vibration and illustrate that for the water molecule. Now, for the water molecule, I ought to have 3 vibrational coordinates. It's a nonlinear molecule, so there ought to be 3n minus 6 independent coordinates of vibration. The energy of the molecule doesn't change if I translate the molecule in the x, y, or z directions. And the energy of the molecule also doesn't change if I rotate the molecule along different rotational axes. And so I subtract out 3 translations and 3 rotations, unless the molecule's linear and then it only has 2 rotations. And I get 3n minus 6 possible vibrational modes that could change the energy of the molecule. So water has 3 atoms, and we expect 3n minus 6 is 9 minus 6 is 3 vibrational coordinates. And if I compute those by forming a force constant matrix, diagonalizing it, getting the normal coordinates, I can illustrate them here. The first coordinate is the so-called symmetric stretch. And you notice all the atoms are moving with the same frequency, like we mentioned a minute ago. The symmetric stretch just means it's symmetric. The OH bonds are both getting bigger or both getting smaller at the same time. You'll notice oxygen doesn't move very much. It's a heavier element. And in normal modes, you keep the center of mass fixed at the origin. So if the 2 hydrogen atoms move up a little bit, the oxygen needs to move down a little bit to compensate and keep the center of mass fixed, but because it weighs so much more, it doesn't have to move very much to accomplish that. The next mode is the anti-symmetric stretch, and I think you can see why it's called that. It's no longer symmetric, and similar comments apply as before. Everything is moving with the same frequency, and the oxygen is moving less than the hydrogens. Finally, the third mode is the bend motion, and it's just bending the bond angle back and forth. Again, if both hydrogens move up, the oxygen moves down a little bit to compensate, but it doesn't have to move very far. And you'll notice this one is one that preserves the symmetry of the molecule. Like the symmetric stretch, the bend keeps the molecule with the same symmetry. It still is the same on the left and the right. It's still the same in front of the plane of the page or behind. Whereas the anti-symmetric stretch motion broke the left-right symmetry of the molecule. So we can apply symmetry labels to these if you know a little bit about group theory. The symmetric stretch and the bend are both A1 motions because they keep the C2V symmetry of the molecule, and the anti-symmetric stretch is a B2 motion. It breaks the rotational axis and also one of the mirror planes. Now, as I said a minute ago, we can easily transition to quantum mechanics now because we have a separable Hamiltonian. And if you remember anything about quantum mechanics and separability of Hamiltonians, you'll remember that when I have a separable Hamiltonian, the solutions are easy. They're just products of solutions of the individual components for the wave function. So the wave function is a product of individual wave functions for each coordinate, and the energy is just a simple sum of energies appropriate for each coordinate. So the vibrational energy is a sum over all these normal coordinates, and in each term I get h bar times omega I, the frequency of the ith mode, times a half plus v sub I, where v sub I is the number of quanta in that vibrational mode. The so-called 0 point energy is where there are no quanta of vibrational energy, so all those v sub i's are 0, but nevertheless, because of that 1/2 term, I still get a vibrational energy, and that's due to the uncertainty principle. Now, how would I get harmonic frequencies for a molecule? Well, essentially I just do this procedure we kind of outlined using quantum mechanics instead of the classical mechanics we started with, but the procedure is basically the same. So I form this force constant matrix. Now I'm using quantum to get the force constant matrix instead of classical mechanics, but it's the same set of equations. That Hessian matrix, I diagonalize it like I did before, and the frequencies, omega I, the angular frequencies, are just the square roots of the eigenvalues, lambda I. What are those force constant values? Well, they're just the second derivative of the potential energy with respect to these mass-weighted coordinates. Now, what is the potential energy? Well, that's just the electronic energy. Recall in the Born-Oppenheimer approximation, the energy that the nuclei feel is the electronic energy that you get from solving the electronic Schrödinger equation with Hartree-Fock or CI or whatever. So to get the second derivative of that potential that I need for the force constant matrix, or the Hessian matrix, I compute the second derivative of the electronic energy with respect to these mass-weighted coordinates. How do I do that? Well, normally what I will do for simplicity is compute the second derivative of the electronic energy with respect to Cartesian displacements, and then I transform from the Cartesian displacement set of coordinates to these mass-weighted coordinates by doing a very simple mass weighting. I just use a matrix m to the minus 1/2 on either side of this force constant matrix in Cartesians, and that m to the minus 1/2 matrix is a very simple matrix. It's just a diagonal matrix. Everything's zeros except along the diagonal, and those elements, the first three elements are 1 over the square root of the mass of atom 1. The next three elements are 1 over the square root of the mass of atom 2, and so on and so forth until you run through all 3 n elements of our mass-weighted coordinates. So I form the force constant matrix in Cartesians, I transform it with this m to the minus 1/2 on either side to get the mass-weighted coordinate force constant matrix, and then I diagonalize it. Now, when I'm getting my second derivatives of the energy in Cartesian coordinates, how do I do that? Well, if we're lucky, somebody has worked out the equations with pencil and paper of how you analytically compute the second derivative of the electronic energy with respect to two Cartesian displacements for whatever theory you're using, Hartree-Fock or perturbation theory or whatever. But these equations can be quite difficult to work out for higher levels of theory. And even if they have been worked out on pencil and paper, it doesn't mean that the computer program you're using has those analytic equations coded up. If we're either missing the formula or we're missing the code, we can compute the second derivatives numerically as a finite difference of energies or gradients. So in this last equation, I'm showing how we can estimate the second derivative of the electronic energy with respect to two of these Cartesian displacements, x for atom alpha and y for atom beta, as a difference between two gradients of the energy with respect to y displacement on atom beta, where I evaluate that gradient plus or minus shifts on the x alpha coordinate. So this is a generalization that the gradient is approximately delta y over delta x, but now we're saying we just do that one more level, and the second derivative is approximately delta gradient over the shift in the other coordinate. In general, I recommend using the analytical Hessians when you have them. There are a few reasons for that. The numerical and analytical Hessians ought to take you about the same time, so it's not necessarily a time difference question. And just to give you a sense of the times we're talking about, if I do a very simple Hartree-Fock 631G star calculation on the benzene molecule, on my desktop I can run the energy in less than a second. The gradient takes a couple seconds, so it takes longer, but not a huge amount longer. But the frequency takes 57 seconds. So the frequencies are absolutely more costly than an energy or a gradient. And one way to think about that is if I do compute it numerically, then if I do this delta gradient over delta shift kind of formula I had on the previous slide, I might need to go plus and minus for every one of the 3n coordinates. And so I need about 6n gradient calculations. And so if n is large, then you can see that the Hessian is way more expensive than a single gradient or energy calculation. Sometimes I can cheat and reduce that number if I have point group symmetry. I can see that some of those displacements will be equal to certain other displacements if I have mirror symmetries, for example. But nevertheless, it's still much more costly. So the main reason I'm recommending analytical Hessians over numerical Hessians is that the numerical Hessian is subject to numerical noise. Because I'm doing this delta y over delta x type approximation, I have small changes, delta y, in the energies or gradients that I'm computing, and I'm normally taking small step size, delta x, in the denominator, so I'm dividing a small number by a small number, and I have to be very careful about numerical precision. If I make the step size too large, then it's no longer a good approximation to the Hessian. But if I make it too small, then I get very tiny numerators and denominators. So typically, if you are doing numerical approximations, you want to crank up the convergence on your energy or gradient to make sure you have a lot of digits to work with when you're trying to do this delta y over delta x type approximation. Another very practical problem that can happen is that if I do one of these displacements and compute the gradient at displaced geometry, sometimes I land on the wrong Hartree-Fock solution at that displaced geometry, particularly if I start from a highly symmetric molecule and then lose symmetry. If that happens, I'll get discontinuities in the surface, and I'll get really, really large, unphysical values for my Hessian. Now, just to say a little bit about how likely are you to have analytic derivatives when you're doing computational chemistry. If it's Hartree-Fock or DFT, you're pretty likely to be able to get analytic gradients as well as analytic Hessians. If you're doing configuration interaction, then some programs do have analytic gradients, but it's pretty rare to find analytic Hessians. Couple cluster, if you're lucky, you'll have a program that has gradients. Several of them do. Hessians are pretty rare. MP2, likewise. If you do some fancy non-dynamical correlation method like complete active space self-consistent field, CAS-SCF, some codes do have gradients, but Hessians would be pretty rare. Configuration interaction or equation of motion coupled cluster for excited states or time-dependent DFT for excited states. Some codes have gradients for the excited states, but it's kind of unusual to find analytic Hessians for those unless maybe it's CIS. Here I'm showing the approximate average errors in harmonic frequencies using polarized double or triple zeta basis sets with various methods. Hartree-Fock tends to overestimate harmonic frequencies by about 10 or 11%. Configuration interaction can be off by around 5%. Couple cluster can be off between about 1 and 4%, and couple cluster with perturbative triples can be off between about 1 and 3%. Now these errors are errors versus so-called experimentally deduced harmonic frequencies. But the harmonic oscillator approximation isn't exact for real molecules. And so in real molecules we have anharmonic effects, and that will cause differences of an additional 2 to 3% for experimentally measured frequencies compared to computed harmonic frequencies. The right way to fix this would be to include anharmonic effects in our calculations, but that involves approximating third and fourth derivative contributions, which are very costly. So you could do that for a small molecule if you want a very careful comparison to experiment. Otherwise, a lot of times computational chemists kind of cheat and either just ignore this additional 2-3% error, or they use scaling factors, and they say, well, we're typically off by, 3%, and so we'll just multiply all our frequencies by 0.97 or something like that. And that'll definitely get you in the ballpark, and for many applications that's totally fine. In fact, a lot of times, if you just need an approximation, these errors are small enough that people just don't worry about it. Now, let me give an example of computing vibrational spectra and how that can be useful. So here I'm showing something I worked on when I was a graduate student. There was detected some isomer of SiC2H2, and it wasn't clear which isomer of SiC2H2 was detected. And so I did some calculations using a polarized double zeta basis set and a couple cluster, CCSD parenthesis T, to simulate the spectra and then try to see if one of them matched experiment better than another. So I've got these two different isomers in blue and in green, and I'm showing their spectra, and then the experimental spectrum is in red. And a lot of times molecules, especially if they're larger, have so many peaks, it's a little hard to tell what matches or what doesn't match or how to assign peaks. In this case, I have several cases where I have a red peak with a nearby green peak and a nearby blue peak, and so it's hard to know which one is really a better match. But if I look at the intensities of the predicted peaks are definitely a better match between the red and the blue. So the cyclopropyne seems to be a better match to the experimental spectrum. Let me mention a little bit more about this idea of scaling frequencies. That's commonly done, and within the right understanding of what that'll get you, which is a little bit improved performance. It's fine. And a lot of people think, well, gee, if I'm scaling the frequencies, I should also do that when I'm computing zero-point vibrational energies, because after all, in the harmonic approximation, the zero-point vibrational energy is essentially just 1/2 the sum of the frequencies times h bar. And so if I scale the frequencies, I should scale the zero-point energy. Well, there's an interesting paper from '91 that shows that this is not necessarily the case. And if you write out the energy of a vibrating molecule, G sub V, where V is the number of quanta in each vibrational mode, then you have a harmonic piece, which is this first piece, plus an anharmonic correction. And we sometimes ignore the anharmonic correction, but it's there in reality. And so what this paper does is it just makes a very simple point. It says, suppose I am interested in the zero-point energy, where all the vibrational quanta V are all zero. So I could compute G0, and I'll have a harmonic piece, which is 1/2 times the sum of all the vibrational energies, omega sub r. And I can get that with harmonic oscillator. But then there will also be this anharmonic correction, these chi terms. So the paper says, well, suppose I used a harmonic approximation to the zero-point energy, and I got the difference between that harmonic approximation and the true zero-point energy with V equals 0. Well, that error from using a harmonic value for the zero-point energy is this equation that I've given you with some of these chi's. Then suppose I'd say, well, instead of using a harmonic approximation to the zero-point energy, I'm going to use a fundamental frequency approximation, where I'm using the true anharmonic frequencies, which is what I'm approximating if I do a scaling of the harmonic frequencies. So if I scaled my zero-point energies, I'm approximating this fundamental ZPVE. And what we see by doing the math is that the error in an approximation like that also involves these chi's. And you'll notice there's the second terms, the chi RS's, the off-diagonal ones. I have an error which is either plus or minus a quarter of the sum of those. But that first term, the diagonal terms, if I use a fundamental approximation to the zero-point energy, I'm off by minus 3/4 the sum of the diagonal pieces. Whereas if I use a harmonic approximation to the zero-point energy, I'm only off by 1/4 of the harmonic piece. So my error actually goes up compared to the true zero-point energy if I scale the frequencies to get a fundamental estimate of the zero-point energy compared to just the unscaled zero-point energy. So the upshot of the paper was that if the zero-point energies that you're primarily concerned about, then the scaling idea might be a bad idea. And if you are going to scale them, it's probably better to use a different scaling factor than you do for the frequencies. Another reason to calculate vibrational frequencies for a molecule is to characterize your stationary point. So a stationary point is a point on the potential surface where the gradient is 0 in all directions. But even if I have that, it doesn't necessarily tell me if I'm in a minimum or a transition state or a higher order saddle point. So if I compute the vibrational frequencies, I can find this out. When I compute the vibrational frequencies, I just count how many imaginary vibrational frequencies I have. Those correspond to negative force constant eigenvalues. And that tells me what kind of stationary point I'm at. So if I have 0 negative eigenvalues or 0 imaginary frequencies, then I'm at a minimum, and the Hessian index would be 0. If I have exactly 1 negative eigenvalue, the Hessian index is 1, and I'm at a transition state. And if I have more than 1 negative eigenvalue, then I'm at some higher order saddle point, which is normally not chemically meaningful. Finally, let me wrap up by giving an example frequency calculation on water using Psi4 to show you what the input would look like, what the output looks like. So here I've got a very simple input for water. I've guessed some bond lengths and bond angles. I set the basis for 631GD, so it'll be a simple calculation. We'll just do Hartree-Fock. So I'll optimize it with SCF or Hartree-Fock, and then I'll immediately compute the frequencies, and it'll go ahead and use that optimized geometry for that. If you want good frequencies, you really ought to be running those at an optimum geometry where you're at the bottom of the well. Otherwise, you need to take some pains to try to project out non-zero gradients, which some programs can try to do for you and others don't. But typically you want to optimize the molecule first, and then at the same level of theory, then compute the frequencies. So here's just a summary of the optimization. My guess geometry was very good, so it only takes 3 steps, and it seems like a clean optimization, and all the criteria converge very nicely, so no problems with that. Now, if I look through the output, what I'll find is a section called the coupled perturbed solver. You solve the so-called coupled perturbed Hartree-Fock or CPHF equations, and that's needed for an analytic second derivative of Hartree-Fock, or if you were doing DFT, you'd solve the coupled perturbed Kohn-Sham equations. And this is where a significant amount of the work to compute the second derivative will go into. And in this case, you can see it converges cleanly, so everything is fine. And then finally, the program will mass weight that Hessian matrix, diagonalize it, get the normal modes, the eigenvectors and eigenvalues, and print some kind of summary for you. So for water, there's only 3 vibrational modes, as we've already seen. Here's a summary table that gives you the frequencies in wave numbers, the irreducible representations if it has point group symmetry. So here I've got my 2 A1 modes and a B2 mode. Some other values as well. The infrared intensity in kilometers per mole, so that's useful. And then at the bottom, it's giving you a little bit of information about what those normal modes look like. So for each atom, it's showing you its x, y, and z displacements in the normal mode coordinate. And you notice those coordinates are symmetric or anti-symmetric because it is a symmetric molecule. Finally, if we have the vibrational frequencies, we can compute a thermodynamic analysis. And that's the topic of a different lecture, but I'll just go ahead and point out what the summary is showing here. The first thing in this summary is the 0-point energy, so it's just summing up all those normal modes and adding up all the vibrational frequencies, multiplying by half, adding that to get the 0-point energy. The 0-point energy doesn't have a contribution from translations or rotations. It's a vibrational correction, so the non-zero values are there for the vibrational part. And then it gives you this total correction to this, for the 0-point energy. And then the program helpfully also goes ahead and adds that to your electronic energy so that you could have a 0-point energy corrected electronic energy if you wanted that for computing a barrier height or something. Next, I'll show you the summary for the enthalpy or the Gibbs free energy. The enthalpy is going to have your bare electronic energy, that 0-point correction, and then other corrections like corrections for finite temperature. And so here you see there are translational corrections, rotational corrections, and then the vibrational corrections as well. And then I add all that up and get an enthalpy at whatever temperature I tell the program I want. Normally they'll default to 298 K. And then we can also compute an entropy and then subtract that times the temperature from the enthalpy to get the Gibbs free energy, and you see that as well. I'll caution you, in most programs, the thermodynamic table will only give you the corrections to the bare electronic energy from translations or rotations or vibrations, and it won't go ahead and add it to the electronic energy as this particular program, Psi4, is doing for us. So you have to be very careful if you run a second derivative calculation, you see an output like this and it tells you the Gibbs free energy is this, it normally means this is the translational, rotational, vibrational correction to the Gibbs free energy that then must be added to the electronic energy to get a total Gibbs free energy. And that Gibbs free energy will be an absolute Gibbs free energy, not a Gibbs free energy of formation, like you might see if you look up delta GF in a table. Same thing goes for enthalpy. So one has to be really, really careful grabbing these numbers out of outputs of quantum chemistry programs, which don't normally explain all this in the output. The user has to just be aware of what's going on. And then finally, I'll just mention there are some nice programs like WebMO that will animate these vibrations for you. We've already seen that for water. They'll also simulate the infrared spectrum for you using just a very simple Gaussian broadening of the peaks. And it's very nice to be able to look at an approximate spectrum or these vibrational modes. I think it gives a lot of insight if you do that. All right, that's all I have to say about vibrations. Hopefully this helps you understand a little bit more about what they are, the mathematics behind them, and also how they are computable by quantum chemistry programs.